So the title of the talk is Surveying the TeV Gamma Ray Sky with the HAWC Wide Field Observatory. And just a quick introduction on Petra. Petra is currently the director of the Earth, Planetary and Space Sciences Institute and also a professor of physics at Michigan Tech University. And Petra is an expert on particle astrophysics and has had a long career in the study of gamma rays and cosmic rays. Petra's background is in astrophysics and also in elementary particle physics, and her PhD, in fact, was in particle physics on the Opal experiment at LEB at the University of Hamburg and Daisy in Germany. Previously, in addition to working on Opal at CERN, and then later Petra joined the HIRES and Milagro experiments as a postdoc. And then most recently, she has been involved in the analysis of Milagro data and the design and construction of the HAWC Observatory at the Sierra Negra Mountains in Mexico. And Petra is going to be telling us about the HAWC Observatory today. She's currently the US spokesperson for HAWC, and she's also the vice spokesperson of the Southern Wide Field Gamma Ray Observatory, SWGO, and maybe you'll tell us a little bit about that as well, I'm assuming. And Petra's science interests and focus is on galactic astrophysics, the study of the Geminga halo, and also on the cocoon analysis and various other topics that are of high interest in the galactic astrophysics world. So welcome, Petra, and thank you so much for giving us this talk, and please go ahead. And I just want to remind everyone that we are recording this session.
Yeah, thank you very much, Rashmi, for the introduction and also for the opportunity, the invitation, and giving me the opportunity to talk about some of the most recent HAWC results. I will maybe give a small, tiny outlook for SWGO, but really only one slide. So, in fact, as Felix mentioned earlier, currently we have a workshop going on at this time, yesterday, the day before yesterday, and today, to discuss, opportunities of collaboration with our LASO colleagues who are also very interested in building an instrument in the Southern Hemisphere or contributing to the construction of an instrument in the Southern Hemisphere, which for obvious reasons is, very interesting to study pevatrons there. Anyway, so back to HAWC though. So here you see a picture of the HAWC main array or core array that consists of 300 big water tanks. They are about 5 meters high and 7.5 meters approximately wide. And they use the so-called water Cherenkov technique in order to detect showers from both gamma rays and cosmic rays. And then we actually have two paths of analysis where we where we study the gamma ray sky, and then also we study the cosmic ray sky. I will only be talking here about our gamma ray analyses here. The energy range that we measure with these with this detector array is between 300 GeV to greater than 100 TeV, and the angular resolution that we achieve with this detector configuration is at the lowest energy 1 degrees up down to 0.1 degrees at the highest energies. I also should mention, in case you attended the Epiphany meeting, a lot of these slides, if you were there, I showed there, but I added a few on to this for this occasion. All right, so let's see. So also, just to give you the complete picture, I'm sure a lot of you are aware of this. There have been recently operated several particle detection arrays with the goal to detect very high energy gamma rays over the past decades, and I'm listing them all here. So there is, as Rashmi mentioned, the Milagro detector for which I worked as a postdoc, and then the Tibet AS gamma array, which has been in operation since 1990. And then we have also the Argo array, and then also HAWC, which has been in operation since 2013. And then, of course, the latest edition with an excellent sensitivity to the ultra high energies of gamma rays is the LASER detector, which has been in operation since 2019 with a partial array, and now is about complete. All right, so what are the features? What are the main advantages of instruments like HAWC, like LASER? And I try to summarize this in this slide here. So there are three main features that make them very useful, I think, for the study of gamma rays. That is, number one, the high duty cycle of these instruments. Oftentimes it is set 100% uptime, but of course you have things like repairs and maintenance and things like that. So it's typically, though, 95%, above 95% uptime that we can achieve with these instruments. And in fact, during the COVID pandemic, we were able to pretty much remotely operate the HAWC detector, which is really a nice thing to be able to do. We had a couple hiccups here and there when repairs are needed, but for the most part, we were able to continue operation. And I think looking at some of the uptime plots that I have seen from LASER, that is true for them as well. And this allows you to measure transients in particular. Then the second thing is the wide field of view, which makes these detectors particularly well suited for extended and large scale emission. And then also a good to excellent sensitivity and good angular and energy resolution above 10 TeV, which of course makes them well suited to measure the highest energy accelerators in our galaxy. A couple more words about the wide field of view. HAWC almost continuously observes the sky as it transits over its zenith, and you see that here in the left picture here, the celestial coordinates, and what is shown here is the instantaneous field of view of HAWC as it progresses to the left. So that is a nice feature. The field of view is about 1.8 steradians, about 15% of the sky. Once you actually come to surveys and you combine all the data, surveys for DC sources, I should say here, then you have a sky coverage of about 2/3 of the sky, and that's shown here to the right. This is the resulting exposure in galactic coordinates, and it shows you here the sensitivity, not our latest sensitivity, I should say, but the 507-day sensitivity that on which our second HAWC catalog from 2017 is based. This next plot is now showing the sensitivity versus energy, and two things are really interesting to see here. So again, this is our 507-day sensitivity on which the second HAWC catalog is based. What's interesting to note here, so this is the second HAWC catalog, this is an actual measured sensitivity. So sometimes you will see where the HAWC sensitivity goes up at the highest energies. That was based on early simulation studies where we did not take into account the full possibility of doing gamma hadron separation. So that's why this looks so much better here now in this paper. And then in this paper, we also presented the projected sensitivity after using 5 years of HAWC data. And this is interesting to note because this will be the sensitivity of our upcoming HAWC catalog, which is in preparation. That means we will be using more than 5 years of data and then also have the ability to, we had in the meantime the ability to improve our data reconstruction. So in fact, you may be able to expect something a little better than this dashed line. And then you see here the crossovers, for example, with Veritas at slightly below 10 TeV for these sensitivities. For here we compare to 50 hours of each of these instruments. Okay, so yeah, so what I will be talking about now in my presentation is the things that show what we are able to achieve with these three main features of particle detection arrays in the case of HAWC. So I will be talking a little bit about source searches, the third HAWC catalog. So that is thanks to our survey capabilities. I will also be talking about the new source classes, halos. Then give a little bit of a, if you will, a historic background of this. Then briefly mention northern Fermi bubbles, molecular clouds, and diffuse emission, although I will not be talking that much about those. And then I will finally also be talking about our searches for Peritron. And in fact, in 2020, we published a paper listing several Peritron candidates that then also, like all of them were then also seen at even higher energies by the LASO instrument. And then I will just briefly, flash some results that, are tests of fundamental physics in a unique phase space. Okay, so, and then this will be not always, in this order, but all of the coming results can be categorized in these three classes or groups. Okay, so this here is the HAWC sky as seen in the 3HWC catalog. The catalog is based on 1,523 days of data. That is about 3 times the exposure of the previous 2HWC catalog at above several TeV. So the sensitivity curve that I showed you earlier. So it's in between the dashed and the solid line. In this catalog, 65 sources were detected above 5 sigma. 20 of them were at least 1 degree away from previously detected TeV sources. And then 14 of these have potential counterparts in the 4th Fermi catalog. Now, these are a couple more plots from the 3HWC catalog paper. What you can see here is these two here show the distribution of sources along latitude and longitude of our galaxy. So you can see obviously the majority of the sources are distributed along the galactic plane. And then what you see here in this figure here, that due to its location, HAWC is most sensitive toward the galactic anticenter region and to the inner galaxy. This here is the sensitivity curve for HAWC, overlaid again with the distribution of sources. And so these pink, the pink distribution shows the distribution of the 3HWC sources, and then the dark distribution here shows the sources that were discovered newly with respect to the 2HWC catalog, which was about 37 or 38 sources. And then another thing that you see here is the head-on view of our galaxy, and showing the locations of HAWC sources with their differential flux at about 7 TeV in color coding here, overlaid with our galactic plane. The thing that we learned from the 3HWC catalog is that a significant fraction of the 3HWC sources were found near pulsars listed in the ATNF catalog, and 2 of these that I'm showing here, that I'm listing here, have not previously been connected with TeV emission. So lots of new things to learn. Then another thing that's interesting to mention in this context, since we also looked at in our catalog study, we looked at association with a so-called new source class, that is HALOs. So in 2017, HAWC reported the detection of extended gamma ray emission coincident with locations of two nearby middle-aged pulsars, that is the Geminga pulsar and then the pulsar inside the monogem ring. And then what was new in this analysis is that we, instead of previously what we always would do is, fit Gaussian to our emission in our maps, and then or a disk, and then either it would be a Gaussian representing our point spread function, or a Gaussian which is extended, indicating that the sources are extended. Then we also sometimes, like I said, fit a disk emission, and of course we all know that that is not what that's how you can approximate things, but that's not necessarily what really is going on in space. So we made a first attempt at fitting a more phenomenological model that allowed us to kind of extract more directly the diffusion coefficient of these particles. So that's what's shown, that these red fits here are due to this more phenomenological fit that is done due to the surface brightness as seen in the HAWC map. And what I wanted to show you here again, wide field of view. This is the distance out to which we fit the emission around the pulsar, so 10 degrees in both cases, essentially. The observation then demonstrated that these pulsars are indeed local source of accelerated leptons, and the surrounding emission profile can be used to constrain the diffusion particles away from the source, which then led for us to a much slower than previously assumed diffusion. Now, since then, of course, a lot has happened. Models became more sophisticated. The Geminga halo discovery and the discovery of several other extended pulsar nebula has then led to the hypotheses that extended halos are a common feature of pulsars, and there are several papers that I listed here if you wanted to take a look. The interpretations are somewhat variable. I only give here two examples here and here. These are two little schematics from two different publications. The idea of these interpretations is that the observed gamma ray emission is due to inverse Compton upscattering of cosmic microwave photons by relativistic electron positrons that have escaped the classical pulsar wind nebula, but remain trapped in a larger region where diffusion is inhibited compared to the interstellar medium. And that's kind of this very simple schematic here. And then other interpretations say, for example, that they are only found around very old pulsars, at least 100 kiloyears old, where that either have left the supernova remnant shell, or whose supernova remnant shell already dissipated, which allows these electron positrons, these leptons, to diffuse freely in the vicinity of the pulsar. And that's kind of sketched here in this right-hand sketch. I think what is common to all of these interpretations is that we do say there's this distinct structure, which is distinct from classical pulsar nebula that we see in X-ray. And that because this leptonic plasma has escaped from the direct X-ray pulsar nebula. Okay, and then since all of this happened at TeV, people started looking into Fermilab data at VeV energies, and also there then were able to distinguish gamma ray halos. And so that's why we started out calling them TeV halos, but they are really now called gamma ray halos. So back to the 3 HWC catalog. using similar criteria as in one of the papers that are listed above. A list of pulses is created with the 3HWC catalog. And the idea is that they are likely candidates to have a TV halo. With that, we identified, and then of course we looked at the age. Then we needed to look at declinations where HAWC was sensitive enough. And then also we looked at, in particular, cases where the spin down flux of at least 1% of the Geminga pulsar was reached. And so with that, of the 16 such pulsars, 8 are especially coincident with at least one 3HWC HAWC source. So that, and then associated or coincident means here within 1 degree, which is granted relatively big region. Further, this year, another study was done where people in HAWC were trying to understand if ultra high energy gamma rays are a universal feature near powerful pulsars. For that, they did again a vicinity study, if you like, of highest energy gamma ray sources that are not of the high energy gamma ray emission near a set of sources that was selected, extremely powerful pulsars that was selected. And so the criteria for these, to identify these 10 extremely powerful pulsars that were then used as a data set for this sub-threshold search is listed here. So in particular, the spin down energy or power rather was greater than 10 to the 36 ergs per second. The search was limited to the inner galaxy in HAWC's field of view. So we looked at a region along the galactic plane of ±1 degree, and then we looked between 5 degrees and 90 degrees in galactic longitude. And then we also excluded known ultra energy sources that are about 1 degree away from these or regions of about a circle of about 1 degree radius around known ultra energy sources. So this is the result of one such search. So there were different models, or also in one case no model assumed. They take into account, so this fit was done, this joint fit, they were all summed up, and then a joint fit was done of all these 10, the emission in these 10 sources. And then with this AI, A sub I, different models were tested. So no model that is just set to 1. And then in one case, we tried to take into account the distance of these pulsars by setting this A to 1/d squared. Then another model, the spin down power was taken into account, the inverse age, and also the flux at 7 TeV was fixed. So these are then the TS values that we got in these 3 different energy bins. And you see that the detection was in most of the cases above 3 sigma. For the first 2 energy bins between 56 and 100 TeV and 100 TeV and 177 TeV. So the conclusion here then was that, yeah, if you look at a set of these selected pulsars, it appears that there is evidence for emission in surrounding these sources. This is of course a rather crude method, but it's certainly an interesting indicator. Another study, though, in parallel or at about the same time that we performed, was trying to understand if emission that we detected around the boomerang region or in the boomerang region could be due to, could be powered by Peritron in that region. So what was done here is the very high energy gamma ray emission with HAWC, as you see here in the central map, was detected above 100 TeV significantly. The excess is well isolated and inconsistent with background fluctuations at the 6.2 sigma level pre-trials and 4.3 post-trials when you consider HAWC's entire field of view. The right figure then here shows the best position of the HAWC source coincident with the boomerang region. And it's consistent with the very high energy detection by Veritas and Milagro, and also with the pulsar position within uncertainties, of course. So that's shown here to the right. And the pink contours that you see here indicate the 1.4 gigahertz continuum brightness temperature from the Canadian Galactic Plane Survey, and then also overlaid, this whole thing is overlaid with the heat map of molecular column density. Now, what we then did for this paper that was published also in 2020 is, number one, we confirmed that there is an extent of the HAWC, which of the HAWC 20 of this HAWC detection, and that is constrained to less than plus minus 2.3 degree, 0.23 degrees. This morphology then, this is what we confirmed, this morphology is consistent with the Veritas detection. So given that, then a joint Veritas HAWC spectral fit was performed, and it was well fit by a power law with a gamma of with an index of minus 2.3 between 0.9 and 180 TeV. The emission can be interpreted to be originating from protons with a lower limit in their cutoff energy of 800 TeV. Most likely source of the proton at the time was thought to be the Supernova Remnants G106.3 plus 2.7. But also, I mean, this was all statistical fit. There was a slight preference, but a purely leptonic origin of the observed source could not be excluded at the time. Since this publication here, the Tibet AS gamma detector and LASO also reported emission above 100 TeV and reached similar conclusions. For example, the Tibet AS gamma paper, they also tried to fit a model and reached a very similar conclusion to what was presented in this HAWC paper. But one of the things that struck me as, you know, knowing the HAWC paper and then also reading the Tibet paper is really what we do need is a deeper morphological study to truly understand what the origin of this gamma ray emission is. And who knows, hopefully this will be provided by LASO. We shall see. Or by HAWC, hopefully, but it's really, this source is really north for us, so it's going to be ambitious. Speaking of supernova remnants, maybe versus pulsar nebula, if you like, or pulsars. I shouldn't say versus, but we also looked at supernova remnant that were the candidates that were detected at GeV energies by Fermi. And then we selected 10 of these that were in the HAWC field of view. This is kind of shown here. This is a contribution to the last ICRC by Henrike Fleischert. And what she found is that when she looks at these regions of non-significant detections or no detection, she would end up with, if she assumes the same morphology as seen in GeV gamma rays, she would end up with no evidence of such subthreshold TeV gamma ray emission in this sample. I should also add that Henrike did do combined fits of regions where we do see emission, for example, gamma Cygni, but also there it appears that the spectrum cut off below 10 TeV, I think, about thereabouts. Anyway, there was no extension to very high energies. Further on Peritron Searches, this is this paper that I alluded to from 2020 that presented several source detections that we then dubbed HWC, as in very high energy. And above 50 TeV, the sources that we detected are listed here. And then above 100 TeV, about 3 remained very significantly emitting, although you see, so these, we made a relatively strict requirement that they had to emit at about 5 sigma above that. And so this here, for example, disappeared, even though you see that there's still emission in the same location. So it didn't disappear, but we didn't include it in our list of those. So, so then, since the publication of this paper, we then looked with more dedicated analysis at each of these regions. So we looked at the cocoon region, we looked at the dragonfly region, we looked at the 1907 region, which you can see is really very, very bright, and similar to this source 1825, all of these we looked at with multi-component fits, and they have been since published. In the following, I will only summarize a little bit what we have seen with the in the cocoon region, and I believe that was discussed in some prior talks in this series, and then I will also talk a little bit about 1825. So the cocoon region. So this is a zoomed in picture with a dedicated analysis. The green dashed lines here indicate the region of interest that we used for our multi-source fitting. So you see here this little region, there's this byte taken out of, if you like, out of this region of interest. The idea here is that we don't want to, in our model, have to include this in our model fit. Although we did systematic studies and they showed that the results were very similar to the finally reported result. And then, so you see this region here before subtraction of the 3 sources that we modeled here. That is, we modeled a source that is co-located with gamma Cygni, then a source that is co-located with a pulsar wind nebula in the region, and then we modeled an extended emission source that is due to the cocoon over OB2 emission that is emanating from that region. And then what you see here to the right is the map, the same map, but after subtraction of the contribution from gamma Cygni and the pulsar wind nebula. And then again, here, this was untouched from this multi-source fitting analysis. This was published at the beginning of last year. And then we see here the spectrum of this, this cocoon component overlaid with previous measurements from Fermi and Argo, and then another study from Aaronian et al. And we see here also the projected radius that's kind of indicated here. We looked at the emission in each of these segments, these annuli around the OB2 star forming region. So the conclusion from this study was that the gamma rays are likely produced by 10 to 1000 TeV freshly accelerated cosmic rays that originate from the enclosed star forming region, Cygnus OB2, likely we concluded that the emission is likely of hadronic nature. And then we also noted that the spectral shape and emission profile changes from GeV to TeV energy, although certainly a bit more data would help in this context. Right, and then two different models it was very difficult. We did not say one or the other is preferred because the distinction here was not big enough between a continuous injection or recent burst model. So again, more data or, especially data up here at the highest energies would be advantageous. So just to give you an idea why multi-source fitting is important, here I overlay this spectrum by hand, granted, with other measurements in the regions. This is in the region. This is from ICRC proceeding where one of my master's students tried to isolate the emission due that we believe is due to the pulsar wind. And then here again, an overlaid like semi-transparent fashion, and you see big difference, right? And that is, we did actually, when the LASO Nature paper with the ultra energy cosmic ray sources came out, we were of course curious to see if the LASO measurement is agreeing with our measurement. The only problem was, of course, in our case, we are looking at emission over a 2-degree radius over, and while LASO in this I believe they are working on morphological studies in this region, but for the purpose of that paper, they reported a flux above for representing a disk of 0.3 degrees. And so we reanalyzed HAWC data, making that same assumption, and found an excellent agreement, almost too good, with the flux reported by LASO. So just as a side note. Another source that we since have analyzed in more detail is this 1825 source. So you see here the measurement. So we resolved, instead of in the high energy catalog from HAWC, where we only reported one source, we did actually a similar thing as LASO did, where we just looked at an extension of about 0.3 degrees. We then resolved the entire region into 3 different sources, the location of which are shown here in this lower left map. And this is 1825, 138, 1825, 128, at 6, sorry, and then 1825, 34. And this here are these 3 sources overlaid with a map of HAWC above 177 TeV. This was presented at the last ICRC, and you can see here in the upper labels, those are the HAWC sources, and the lower labels LASO sources, and the lower labels are the HAWC sources. And you can see again a really nice agreement between the HAWC measurement and the HAS measurement after we did this multi-source fitting. That motivated one of the students I'm working with, a PhD student, to do a study where he combined he wanted to see how well do the spectra measured by LASO and HAWC connect, and you see a really nice connection here about where the nice overlap where the LASO measurement begins and the HAWC measurement ends. So this he also presented at the ICRC. So I think there are good things to come. I honestly really think this is only the beginning of combining data and getting that way more sensitive measurements. There are other recent results of probing our galaxy. I don't want to go into too much detail here because I'm coming up to the 10 to 10 mark, but and a lot of them you probably have seen. There's this measurement where of SS433 with HAWC data that was published in Nature in 2018. that showed particle acceleration is occurring in the jets and not in the central binary engine. Then then also upper limits for Fermi bubbles were reported. I list here, if you are interested, the paper where you can read about that. And then most recently, again, making use of the wide field of view capabilities of HAWC, we looked at a stacking analysis of locations of giant molecular clouds. And you see kind of a summary of the results here compared to, so the expectation here in purple, from assuming that the gamma ray, the cosmic ray C essentially looks like we are measuring it here locally, and then our upper limit measurements are shown here. So we are beginning to become sensitive here. Then also we have an ongoing analysis of galactic diffuse emission that we are working feverishly to publish, but there are still a few things that we need to sort out before we can present some results here. Okay, fundamental physics. Yes, we have measured Lorentz invariance variation and published this in 2020. If you have seen recent talks by Lasso, they have now made these limits that were reported in this paper for this for Lorentz invariance violation much stricter. And then we also reported limits on dark matter signatures from dwarf spheroidal galaxies. But again, moving on here to future improvements, I wanted to spend a few minutes talking about what you can expect from HAWG in the next year or two, maybe 3 years. So we are currently testing a new data pass of main array data. We call that pass 5. Most of the results, just to give you an idea, that I've shown in the previous slides are based on our so-called pass 4. Pass 5 is different in that it features a significant improvement of the point spread function. Then it also leads to significant improvement at lower energies in terms of sensitivity, and may lead to some forthcoming unexpected results over hopefully the next few months. Again, when you have a new pass, you really it takes a little bit of time to understand the systematics of it, and we don't want to report things that then turn out to be just some kind of measurement artifact. So just to give you an idea visually, so this is pass 4 from this 3 HWC catalog. And maybe at first sight, you're like, oh, what's new? But then you really compare these regions here and you see all these structures much more well defined compared to up here. And this is, and also here, for example, this is truly important because because this really helps us with our multi-component fits, which I hope I've convinced you are truly important in order to, get the maximum science of our measurement out of our measurements. Then another thing I wanted to show you is this is kind of a zoom in of one of the regions. So you see something popping up here close to the galactic center. This is, of course, all preliminary, but we are trying to understand this axis here a little better because some of the instrument response functions are really not optimized for doing this, these low declination analysis. So, but this is very encouraging. And then to the left here, this is again the 1825 region with these 3 sources that HAWC has previously resolved. But if you look at what you look at here is a GIF stepping up in energy, starting above 1 TeV, 10 TeV, 18, 32, 56, and 100 TeV. And what you see here, a nice emission popping out at the location of LS5039. So stay tuned. We are currently trying to understand how significant that is at the highest energies. Okay, so right, so we also, of course, given that last map, that last GIF that you saw, we are working also on combining the main array data with outrigger PAS6 data. So it's always like this matter of what do you prioritize, you know, the core array data and getting out, for example, catalogs to the community very quickly, or, you know, spending all your efforts on combining the outrigger array and the main array data. But we are currently also working on PAS6, which will include the outrigger data. First studies that we have performed indicate a mean energy of about 250 TeV along the galactic plane. So again, that is then taking together all the sources, because we have not really sorted out angular resolution and combination of shower front reconstruction and so on. So we are working on that. And then, of course, we are continuing to work on combining HAWC data with data from other observatories, we would like to make HAWC data finally also usable for the community. So to the right here, what you see is a combination or combined analysis, not truly combined, but an analysis of HAWC data of a certain section of the galactic plane compared with HAS data of that same galactic plane section, where the HAS analysis is optimized to detect extended source emissions, kind of making the analysis more like a HAWC analysis. In some sense, that means worse, because the angular resolution is not as good of HAWC as it is for HAS. And one interesting outcome of this was that 7 of the HAWC sources that were previously undetected, as you can see here in the HAS map, 4 of them have now been detected also by HAS. So that shows you, like, combining IACT and PDA data is truly something useful. Yes, and finally, of course, there's SWGO. This is in progress. I think given all the results from LASO, from HAWC in the last couple of years, we really have a good motivation, if I would even say excellent motivation, to build the Southern Wide Field Gamma Ray Observatory. Currently, we are looking at sites in Argentina, Bolivia, Chile, and Peru. And this is the sensitivity for this instrument as reported at the ICRC. This project has been endorsed by the ASTRO 2020 PAG committee as it should be supported by the US science community to some degree. All right, and this is then the outlook. I hope I have shown you that we have ever more sensitive techniques used in HAWC data reconstruction and analysis. And so new source detection and the 4th HAWC catalog approach are imminent. In this 4th HAWC catalog, we are currently working on adapting a Fermi-like multi-source fitting approach. And we have very encouraging results, but that is work in progress. So hopefully you will hear more about this in the next half year or so. Then with HAWC and LASO, we now have 2 instruments with unprecedented sensitivity above 10 TeV that also provide different complementary instantaneous fields of view in the time domain. So that's interesting too. And then, as I alluded to earlier, I think we really do need multi-instrument and messenger analyses to get the best science output, and therefore we are also on this side trying to prepare energy-dependent HAWC sky maps and HAWC tools that can be used by someone who's not a member of the HAWC collaboration. So again, stay tuned on that as well. Thank you very much.
Thank you, Petra. Thank you for the excellent talk. And let's open this up for questions. Massimo, go ahead.
Hi, Petra. Thanks for the wonderful talk. This is really more a general question, maybe naive, and also maybe not only to you, but to the audience. I mean, we've seen, like, from combined HAWC and LASO recent results that most of the ultra high energy gamma ray emission is nearby powerful pulsar. But there are also two outstanding cases, like I'm thinking of LASSO 2108 and 0341, when there is no clear, powerful pulsar nearby. And my general question, maybe naive, is there a way to challenge the pulsar halo scenario, for example, or the PWN scenario, in such cases where we don't have timing information? I don't know, spectrally or morphological from, other wavelengths, from like TV instruments, pointed instruments, or like below that. Because this is really interesting, but challenging, I would say. So.
Yeah, you mean challenge in what sense?
So how do you like, is there a way that in the absence of time information, like, that there's a pulsar there that is probably powerful enough to power the UHE emission? How do you know? Is there a way? Is timing the only way? I don't know. Maybe also to Felix Ruiz, I think is online.
Yeah.
More of a general question, really.
Right. I
think.
Yeah, I think I would think it's hard, but it depends on the sensitivity. Maybe in this case in particular of LASSO, I mean, if we are able to say something about the morphology, but then it's only one of possible scenarios. Without the timing information, it always will be tough, I think. But I would be interested to hear Felix or Ruiz as well. Maybe they have ideas.
Well, I think Elena Amato can address this better than others.
Thank you, Felix. No, okay. So there are a few solid things that a couple of solid arguments that, if you're lucky, allow you to exclude that a pulsar with nebula is at the origin of the emission. The zeroth order one is when you do detect emission which is above the pulsar potential drop, okay? So the straight objection by part of the audience, I guess, will be, but what has the pulsar potential drop to do with it? I mean, usually people we all assume that particle acceleration in pulsar with nebula occurs at the termination shock. So why should it be related to the pulsar potential drop? Well, it turns out that at the termination shock, whatever you do, you cannot exceed the pulsar potential drop. This is easily shown, and with Felix and Emma, we're working on a paper to constrain the emission from some of these sources. So this already allows you, for example, to exclude that the emission that you see from the Cygnus region can be associated with that pulsar. The LASSO emission, the emission that LASSO detected from the Cygnus region cannot be associated with the most likely pulsar, simply because there's not enough energy available. The potential is not sufficient. Then, of course, the other reasoning, which has to do with discriminating whether the emission is leptonic or hadronic, is related to the fact that leptons do suffer losses. So the extension of the source can provide additional straightforward constraints that one can use to exclude. I mean, when you've achieved such high energies, PeV photon energies, then you're seeing the emission. If it is leptons, you're seeing multi-PeV leptons, and the loss times become an interesting probe of the physics. So in some cases, you might be able to exclude the pulsar with nebula origin based on these two arguments. These are the most straightforward ones. Then, of course, with modeling, this basically do not assume any modeling. Then with modeling, you can do more, but you need more assumptions there.
Just in this context, Maybe just to mention, so the 2108 currently also HAWC is looking at an analysis of that region, and maybe I'm not revealing too much, saying that we do see significant emission in that location as well. So I wonder if we were to combine the data from LASO and then HAWC, which goes not as high in energy, but it goes to lower energies, the sensitivity. And then maybe even, you know, Veritas or other instruments. I think that would really be a very nice way of checking these models.
Well, yeah, I guess that some reliable estimate of the size of the source is probably at these energies the best way to discriminate between hadrons and leptons. And also it is true, I mean, if it is leptons, then the most likely sources are indeed pulsar wind nebulae. So if you see PV emission from a region in which there is no pulsar wind nebula, then I would bet on hadrons, right? Simply because I mean, non-relativistic shocks will not achieve that energy for electrons ever, because you are radiation limited.
Yeah, thank you. So this is actually related to a question I had, Petra. You know, you showed the cocoon and you showed some other. There were a couple of sources that were recently published in the Nature paper.
I mean, the LASO Nature paper?
Yes, not the last, the HAWC, this one.
Okay.
Well, the question is, I mean, I guess it's related to what Elena was saying. You know, you've done the modeling and you've considered leptonic and hadronic emission scenarios. How confident are you? I mean, what are your best examples of, let's say, hadronic accelerators, where you have some measure of confidence? Because I guess the situation is not completely clear, right? We don't know.
I would say that's true. The situation is not completely clear. I think we need more data. I think as far as the spatial modeling of the region is concerned, I'm very confident that we can distinguish the pulsar wind nebula and the cocoon. And I think that is important, because that then goes, of course, into the spectral measurement, right? Because we then know that, okay, I mean, at these energies here that we are only measuring the cocoon emission and do not have any contamination from the pulsar wind nebula, which would, of course, then skew your final fit results. But as you see, I mean, going back a little bit more here, I mean, of course, number one, our last data points is a little bit above 100 TeV. So I'm really curious to see what LASO has once they have done some modeling. Also, exactly where their emission ends up. I would be surprised if this 1.4 PeV emission is due to the pulsar wind nebula. But strictly speaking, that distinction was not made yet. At least not from the data standpoint. So I think I think with the next few years, LASO should have a good handle on this, and hopefully we will also be able to make a contribution with HAWC once we have included our outrigger data. But I think another thing I think that's important here is really also, and there I'm interested in seeing LASO combining their data with the WCDA, which measures emission at lower energy. And so, because that's one of the things that that HAWC can do, it goes down to 1 TeV, and then you combine it with Fermi data. And so you have that kind of that range covered. And I fully expect LASO will do the same thing, right? We have people here from LASO who can maybe comment on that, to really then have a fit from the GeV range all the way to maybe PeV, and then that combined with some morphological understanding.
Yeah.
I think at this point, there are indications that it's, like in this case, hadronic, but I think, yeah, more data is always better, right?
Yeah. All right, thank you. So there are some questions from the audience. Evgeny, you had your hands up first. Please go ahead.
Petra, thanks for your very nice talk. My question is about transient sources. They were kind of announced in the beginning of the talk, but so far, as I understand, there are no results. And my question is just to be specific. For example, did you try to do some kind of frame stacking for gamma ray bursts? In principle, during several years, you should have in your field of view thousands of them. And even despite the fact that frame stacking is a tricky procedure, maybe thousands is enough to have some kind of good result.
Yeah, so in terms of transients, the typical, like the usual suspects, Macarian 501 and 521, we have detected. We also have seen flares for Macarian 421, and we are still analyzing this data. There is recently in review is a publication that measures the spectral distribution of measuring the spectral distribution of the flares versus the ground state. In terms of, and then there's also a search for variable emission from an AGN catalog, although that has not really led to very significant transients detection. Now, for the GRBs in particular, we now with PAS5, as I mentioned earlier, we have a better sensitivity, and we got a little excited last year, and then we had to again look at our systematic studies, and then so we are currently repeating that analysis. The main improvement in the lower energies is that sometimes what happens is you have overlapping events, and so with this new pass we are able to distinguish those better. And so again, there I unfortunately can only say stay tuned, but the measurement below 1 TeV is not simple, and you also don't want to have a false positive. So we are currently studying, you know, the false positive rate for this new data pass, and yeah, but yeah, we haven't published GRBs or emission from GRBs yet, only upper limits, that's true. But
okay, thank
yeah.
you.
Mm-hmm.
Thank you. Luigi, I think you had a question as well.
Yes. Hi, Petra. Thanks for your nice talk. So I have one question regarding the pulsar halos as well. People also mentioned how to distinguish this pulsar halo with the hadronic, but so I wonder if you have some progress in measuring the spectrum of Geminga and the Bummer and the other pulsar halo. I think this would be a key to distinguish these two scenarios, right? We expect quite a sharp cutoff of the spectrum at highest energy.
Yeah, and that was something, as I was like, just like 5 minutes before the talk, I'm like, oh, because there is indeed a spectrum that was reported at the last ICRC. I can provide the link to you after this presentation. What they have done is this is a PhD student working with HAUG from Shanghai. Ramiro is his name, and he tried to fit a updated template of halo emission to the spectrum that we are measuring at the location of Geminga, and the conclusions, like the spectrum still has rather large uncertainties, but he was able to fit a combined model, combining, you know, what we have learned from Fermi data to combine that with HAWC data and do a fit of the spectrum. I don't know if that answers your question. I guess maybe what in particular were you wondering?
Yeah, okay. I'll check the reference. Thanks. And another thing is you mentioned about the Cygnus cocoon and the Dassault prospect. What I can mention now is that in the overlapped energy range, the last results they agree well with this HAWC measurement, and yeah, and we are also doing this this multi-source analysis in this region. And so another related question is so how many sources are you using in the multi-source? I saw in your slides this seems quite a lot, right?
For this particular analysis, we are using it may look a lot because we also have labels for OB2 association and so on, right? But for this, like we are looking only in this region of interest, excluding this one here. So then we are using gamma Cygni, the extended emission that we associate with the cocoon, and then the pulsar wind nebula. That's what we did for this paper. But in the past 5, it may be necessary to use more. But we, again, are trying to understand that better.
I see. Thanks so much.
Right. Oh, and I should probably also mention the diffuse emission. In this case, we did a systematic study. So it was not included in the model proper, but we allow for a contribution of about 10% from diffuse emission, you know.
So you mean this the large scale diffuse emission from the plane, right? From galactic plane?
Yeah,
I see.
And I should make one comment about that too. And people sometimes smile at me, but I make this distinction between galactic diffuse emission and diffuse background emission. For me, galactic diffuse emission is truly what we think it is, like what Dragon or Gaprop predicts. And then diffuse background emission is that plus unresolved sources. So in our newest modeling, when we look for source emission, we use diffuse background emission. And then the galactic diffuse emission measurement is a separate analysis.
I see. Thanks very much. This is very helpful. Thanks.
Thank you. Felix, please go ahead.
Yeah, Petra, just one comment regarding the statement that we see fresh cosmic rays in the Cygnus cocoon. It comes historically, I think, from this famous Fermi paper.
Okay, yeah.
But that is not a good. Actually, these are very, very old cosmic rays. I mean, because you need in this bubble to fill them in huge bubble. It's just million years, at least million year, and especially if it's connected to OB, if they're accelerated by OB. So that is, these guys are very old ones, so not freshly.
Agreed.
But I remember this comes from that paper, and it very often is repeated. A question now is, you didn't mention gamma Cygni. What is the situation of the gamma Cygni? I mean, I remember you measured the spectrum, right? Gamma Cygni as well.
Yeah, and I would have to look through old slides again. That was, I tried to find that. I think Henrike Fleischer presented that at a conference a couple of years ago. She since has left HAWC. I believe she when she combined Fermi and HAWC data, the best fit was I think Paula with an exponential cutoff at the time, and the cutoff was around 10 TeV, maybe below, like 7 TeV, and that was what the best measurement was. Is that what you were looking for, like when it cuts off? Or?
And do you continue to work on that source, or you just...
Yeah, actually, I need to touch base with Henrike, because if she does not have time working on this anymore, since she's now working, you know, on Fermi and other things, I will. I'm certainly interested in getting that out as well. Yeah.
Because Magic published also very interesting paper on gamma Cygni, so that
Yes.
could be a thing to combine.
And she overlaid that with the Magic map, and that was with our PASS4 data. I'm kind of curious to see when now that one of the main improvements is really the better PSF, and so it would be interesting to see what the overlay looks like now with the newly reconstructed HAWC data. But yeah, sorry.
Yeah, and the last question, you very briefly mentioned LS5039. So I guess you wouldn't like to now to make a further comment, right? So because about this highest energies, it's very, I think it's coming, it will become very, very trendy. This is my feeling, these binaries. The spectra of binaries going to very high energies unexpectedly, like PSR 1906. So this is a classical binary pulsar. It goes to 40 TeV in HIGRA data, and HIGRA already have seen 20 TeV plus gamma rays from LS5039. So that I just saw you mentioned, but very briefly, that's source.
Yeah. So this is very preliminary what you're seeing here. What we are doing here, this is also a perfect example of how important multi-component, multi-source fitting is. And here in this case, we are trying to apply a method like Fermi does, where Fermi, in that method, what they do is they fit first diffuse background emission to the region of interest, then they keep on adding point sources until the TS goes below 25 or 16, depending on the case. And then they test each of these point sources for extension, and then they do a refit with that final model. And then in the final step, they test the spectral energy distribution of each of these source components. Now, so that's what we are currently working on with this analysis, trying to isolate the emission that is due to LS5039. And for that, in turn, we now are trying to understand, what is the maximum or the minimum maximum emission of that we see from LS5039. You kind of get an idea here, but we want to give this more quantitative value.
Probably minimum will be difficult because 1825 confusion, I guess. And highest will be difficult because of statistics, but there is, I understand, you do detect gamma rays from that source.
I mean, one of the things, if you actually look at this other measurement where we identified this third source, which then looks like it's really spot on with the LASO source, the really big sources though appear to kind of cut off, at least in HAWC data. So, well, let's see. Hopefully that helps with, like, number one, reducing it through the modeling, the contribution at that location, and number two, then also maybe the contribution will not be too big to begin with.
Did you look at the periodicity, because that could help to reduce?
Yeah. So right, and that's we had in previous years, and we did not detect significant periodicity. Now, one thing, we looked at this HAS paper, right, where the high and low state spectrum was resolved. And so right now what we are working on is like dividing up our data into these two classes of emission, if you like, and then looking at the two time period, not periods, but, these two maps, high and low state maps, and see what if it looks similar to HAS, number one, in the overlapping energy range, and then number two, are we able to have maybe one or so or two more data points? I really would love to have outrigger data for this analysis, but unfortunately that's not there yet.
Thank you. Thank you.
Mm-hmm.
Thank you. We have time for one last question, and Paulo, go ahead.
Okay, thanks for a great talk. I just had a question about sources between bands. There used to be a class of HES NID sources. Do they still exist, and are they seen by LASO and or HAWC They could have been pulsar wind nebula for some reason. They weren't showing up at lower energies. Is there anything about that, or some of the sources you presented? Old HES NID sources, or do HES NID sources no longer exist?
Oh, to my knowledge, they still do exist, but maybe a HES person should comment on that. Yes, we have looked at that. These are also ongoing analysis. Again, some of them, I don't want to say too much because again, we are still working on them. Where we looked really at HES NID sources and then looked what do we see in HAWC, and can we extend, for example, the measurement of energies to a little higher energies. So I can tell you that maybe you want to attend some of the APS talks. There might be a couple talks from HAWC specifically looking at some of these HES sources.
I mean, you showed that map.
Yeah.
This analysis was redone with, I guess, with the HAWC point spread function kind of model.
Oh, that one, yeah.
That might pick up some of these sources, right? I mean, that's a better way to compare.
Yeah, I honestly, right now I'm not sure how many of these were unidentified. Is there a HES person here?
Yeah. Okay, we will. I mean, the APS meeting is in New York this year.
Right.
It'll be in person.
Hopefully.
So I don't see any other questions. Any final words? Felix, did you have anything to wrap things up, or we just?
No, just to say that is great. I mean, the comment about the HAWC, it's amazing that they managed to get such, it's unexpected. I'm sure it was a big surprise to many to see such beautiful results. And that gives a lot of optimism for future. And I just want to say that what HAWC was a bit unfortunate, like it reminds me of situation of Agilent, Fermilab, just Agile arrived and immediately Fermilab. So HAWC start to release this result and then LHAASO, right? But anyway, HAWC probably is more or less saturated for next few years. So that is clear and necessary to move to another step. My only the question would be still there's a not full overlap between LHAASO and HAWC. So probably that could be, HAWC could be focused on that part of the sky, because it will be very difficult, of course, to compete with LHAASO. I mean, for coming 1-2 years. But the part which HAWC covers better than LHAASO, maybe that would make sense to, of course, I mean, HAWC looks, observes the entire sky, but maybe for analysis to focus some very specific things like we mentioned LS5039, because local exposure time, and LHAASO maybe needs still some years for those sources. And for strong sources, of course, LHAASO quickly will get all statistics needed. But for these very weak ones, maybe LS5039 still contribution could be significant from HAWC and from the sites which are not the best. I mean, difficult. It's out of the field of view of LHAASO. So did you think about some strategy for coming 1, 2, 3 years for HAWC? Because you need still go for 5 years maybe before the next instruments. So that would be important to maybe to find out the most effective way to use HAWC results.
Right. So certainly the weaker sources, I think it will indeed take a while to resolve them. And that is actually the thing is twofold. The issue is twofold. Number one, the sensitivity at maybe low at the edge of the field of view for LASO, where HAWC is not at the edge of the field of view. That's sensitivity. But then I do believe that the PSF, while it is certainly not as good as IACTs, the 0.1 degree is something that we absolutely profit from in our, number one, in our resolution of sources, but then number two, also then when we do these multi-source fits, that helps really quite a bit. And I say this because I see this now with the step from pass 4 to pass 5 data when we have improved our angular reconstruction. And I don't know if LASO can push the limits there, but it would be interesting to see if they can, because I think 0.1 degree at highest energies is absolutely important. And so that's kind of, I think right now where HAWC will focus on. And then the other thing is, I really, really hope that we at some point can produce FITS maps providing HAWC tools for everyone to analyze them. I think that would go a long way, like Fermi. But Fermi had a whole team working on this, while we don't, unfortunately. But I think I'd be really curious to see what the community makes of our maps. So, and I think the HAWC data is now mature enough, because sometimes when you just started taking data, you really don't want to share it like immediately, because you are still maybe struggling a little bit to understand it. But we are not in that phase anymore for HAWC. I think we are now in that phase where we understand pretty well how things work, and therefore should, you know, hopefully provide more sophisticated science tools than we have in the past, where we just showed, you know, maps, and then you can look, you can type in declinations and RA, and you see the emission from that region. But it should be more than that. It should be more like the Fermi science tools, I think. And I hope that we can get to that. And that is a big job, honestly, so that will keep us busy for the next few years, I think. Let's hope that we have enough resources to do that.
Okay, maybe we have still 2 minutes. Just it prompted me to ask you another question, because do you think just to do something more, a bit different, just to convert the HAWC like gamma ray burst detector, like to go very low threshold, below 100 GeV with special trigger, and they use that for that. If you manage to get very low threshold, then it doesn't matter what is the size, it's just more than sufficient. And so maybe that could be interesting way of using HAWC for future. Just forget about highest energies, just make another trigger and try to go below 100 GeV, or at least around 100 GeV.
Yeah, so that's one thing we are working on as well. That is right now, when we have our like immediate trigger and our immediate source search on site, that's still, the default is still this pass 4 reconstruction. And as I said, we do gain, I don't remember, it was a factor of 2 or something in sensitivity at the lowest energies with this new pass. And so we had a trial run of this pass 5 reconstructor on site. We still need to work out a few kinks here and there, but yes, this is also one of the things we are looking at. It's not quite done yet, but certainly that's in the plan.
Thank you.
All right. Thank you. Thank you very much, Petra. It was really excellent talk and great discussions. And thank you to everyone who attended, and hope to see you in 2 weeks. We have a talk by Elena Amato on the Nebula. Thank you, everyone. Bye.